That's my name. I started Away3D about 5.5 years ago, like I said, with Alex. I've been doing Flash for over 12 years now, I guess. And it's pretty much been my primary program language all the way through that. I also have a blog, infiniteturtles.co.uk, where you can find various ramblings about mainly Stage 3D related stuff these days. And Away3D.com is where our main community is hosted. We have forums on there, showcases of Away3D work, tutorials on how to get into Away3D just getting started, or if you're a bit more advanced effects that you can try. And awaymedia.co.uk is my consultancy company that I run in parallel to Away3D for professional support. So companies wanting to have professional support for any Away3D related projects. And more recently, this year in fact, we also started something new called the Away Foundation. This is a non-profit organization which is designed to manage the various sponsorships and development streams that we have going on at Away3D now. Obviously Adobe features quite largely in that, and it's basically a way of sort of promoting these open source stuff that we do to other commercial companies. So if you are interested in becoming a partner of the Away Foundation, you are entitled to certain benefits and so on for that, and you also get to help us develop new and cool features for the Away3D engine and other libraries that we manage. So the awayfoundation.org is where you can find out about that. One of the recent things that we've done, released, is the Away3D 4.1 alpha version. This is still a little bit rough around the edges, which is why we've called it an alpha. But the point of it is that it has a lot of new features, a lot of which are for optimization. You can do really cool particle effects in it now. There's support for things like ATF textures, which is very cool, and we'll be looking a bit at that more later. So check it out. It's on the Away3D site, and you can also go to our GitHub page and check it out there. The latest sources in the dev branch, you'll be able to find everything for 4.1. So to start off with, I wanted to talk a bit about the history of the GPU. GPU stands for Graphical Processing Unit, and it's something which has been around for pretty much as long as visual displays have been attached to computers. But it's surprisingly not being employed as much as it could be, and certainly in the case of Flash, the GPU wasn't really something that you could access and program until Stage 3D came along in Flash 11. But if we want to really go back to the sort of roots of graphics on a computer, we have to go back a long way to 1958, I believe, when this machine came on. Well, it didn't come on the market. It was used exclusively by the United States military. But it was something that actually used a visual display unit and had a way of interacting with that via this scary-looking device with a gun that you pointed at the screen, and apparently that fired a beam of electrons, which sounds very dangerous, but it worked, and it was used for doing things like radar maps and so on. But this is really just the start of graphics rather than of hardware acceleration. The next thing, which was actually the first commercially available graphical program for a computer, was something called the DAC1, which was essentially a computer-aided design package designed by General Motors and IBM in 1951, I believe it came out. So this is still, 61, so still way in the past, but had the ability to actually draw vectors on screen. And this is where problems started occurring, really, with the way that this worked, because everything was still CPU-driven at this point. So the graphics, the CPU could only do one thing at once. It could either do calculations for interaction or updating the data inside it, or it could draw to the screen. So this was very cumbersome, because if you wanted to see anything, you first of all had to do your interaction, and then it would be displayed on the screen. The two weren't concurrent. So this is where the problems essentially started in terms of how this can be managed in a more effective way. And the first time it was managed effectively was by these two guys. Ivan Sutherland and Dave Evans set up ENS, which is a company that's still going. In fact, you can go to their website, es.com, and they've founded themselves in 1968. So we're still talking ancient history in terms of computers. But the significant thing about this was that they developed the first piece of graphics hardware, actual graphics hardware that was dedicated. Their hardware had routines that were taken from the CPU and actually reproduced in hardware. And they found that this was an incredibly efficient way of programming graphics. You could program things of the order of magnitude of 100 times faster using this method. And what was also significant is their research lab, which was based in Utah University, had a number of very key and influential figures who, became key influential figures over the course of time. These include people like John Warnock, who went on to found Adobe, Ed Catmull, who went on to found Pixar and also developed a whole heap of stuff to do with 3D graphics, such as texture mapping, and now I think is president of Disney or something, so he's done very well. And the founder of Silicon Graphics, who you may have heard of, Jim Clark. And these people ended up being pioneers in their field, but they were all at one point students in this research lab at Utah University. So a lot of things seem to originate from this. So talking about the evolution of where this went, obviously Silicon Graphics were a company that did high-end graphics processing for a very long time. In fact, there was a period of time, I think it was from around 1992 to 2002, so like a span of 10 years, when every single movie that was nominated for an Academy Award in visual effects would be using Silicon Graphics workstations. So they really took the industry by storm in terms of high-end graphics processing. And this was possible because they used GPU technology. In fact, their geometry engine, which was the GPU technology that was in most of their early systems, was a direct descendant of the stuff that they'd done pioneering work in at ENS. You could do quite a lot of stuff with this. But let me ask a question. Did anyone in this room ever own one of these? No, because obviously these things ran into the tens of thousands of pounds or dollars or hryvnia. It was impossible to own one for personal use. And that's the way it was until this came along in 1985. And I don't want to bang on about this too much because I am a bit of an Amiga fanboy, but it was pretty much revolutionary in computer terms for the consumer. For the personal computer, there was, for the first time really, the ability to program graphics in hardware. And there wasn't anything else that had occurred before that. And what's odd about this is that the Amiga really didn't do well in business terms. I mean, it had a great and loyal fan base, but the Mac pretty much eclipsed it. But don't forget, this is 1 year after the Mac. This is 1 year after Steve Jobs got a standing ovation for scrolling monochrome text across the screen. And yet, the Amiga could do this sort of stuff. Okay, you start off with scrolling text, scrolling text, zooming text. That's a bit dull. Let's twist it as well. Woo! Yeah, come on, round of applause for that. I could probably watch this all the way through, but sadly, this isn't just about the Amiga. But yeah, there was a lot of cool stuff that you could do with it, and the reason why was because it had a dedicated Blitter chip. which I think were called Denise, which did a lot of the graphics work that the CPU would otherwise have to have done. So it freed the CPU up for other things. It was essentially the first multitasking machine for the home user. And you could actually program the GPU pipeline, which again was pretty much unheard of in consumer cards at the time. In fact, you'd have to wait about 15 years before that was ever possible again from the sort of PC era. So the Amiga did well, or not, depending on your point of view. But then around 1992, things began to become a bit more standardized. Now, OpenGL is something that we're all familiar with today. But before OpenGL, there was a similar graphics language called FIGS, P-H-I-G-S, which was pretty much the open standard of its day. When Silicon Graphics was doing all its cool stuff with its proprietary hardware, FIGS was the open standard that was used by other people to create more generalized consumer goods. And the problem was that FIGS was a bit difficult to use, and so in 1992, Silicon Graphics open sourced their Iris GL engine and renamed it OpenGL. And this is what we've become to know and love. OpenGL is the forefront graphics language for programming GPUs these days. And especially now that we have OpenGL in a lot of mobile devices, it's almost certainly become the most prevalent compared to DirectX, which is the other competing format out there. But OpenGL is not an open source, but an open spec language, and it is used by pretty much all the graphic hardware vendors these days. And it began to create a renaissance in GPU technology. So the first one to really come out on the market, which was which was a little bit unfortunately dubbed the 3D decelerator because of its terrible performance, was the S3 Verge in 1995. And this had a lot of the architecture that we see in modern GPUs. It had a vertex buffer, it had anti-aliasing, it had video rendering capabilities all built into hardware. But it was non-programmable, and like I say, the performance was pretty terrible. The first graphics card that was actually worth owning, I suppose, was the 3DFX Voodoo, woo, which was very exciting. At the time, its performance actually matched the sort of the premier console of the day, which was the PlayStation 1. So around 350,000 polygons per frame, and per second, sorry. And this was nothing short of a miracle to PC users. They could finally play games on their PCs. They could play Quake at 640 by 480 resolution. It was incredible. And Voodoo themselves, 3DFX themselves, were no strangers to shouting about this.
We have in our possession a chip. A chip that could revolutionize medicine as we know it. By performing 100 billion operations a second. This chip could help us heal across continents.
You sort of know what's coming.
More lives. Help people live longer than ever. And give us all more time to cherish the journey's truest rewards. But then we thought, hey, let's use it for games.
3DFX PC accelerators. So powerful, it's kind of ridiculous.
You know, that game's a little violent for my taste.
So yeah, that's the Voodoo card for you. And sadly, they eventually went out of business. Unfortunately, their business acumen wasn't as good as their 3D hardware. And what's significant about this is that it allowed different cards to come in underneath, which were running on the OpenGL standard. 3DFX Voodoo actually ran on its own proprietary standard called Glide, which was very suitable for the day, but it was a fixed function pipeline, which meant that it was non-programmable. So in a way, if 3DFX hadn't gone bust and carried on, then maybe we'd all be programming in Glide today, who knows? So one of the first actual, or probably if not the first, programmable graphics chips to come out for home computers or for home computer graphics cards, was the NVIDIA GeForce 3. Now, this came out in 2001 and had something like 30 million polygons per frame, per second. And was pretty much like a mini revolution of it on its own. And it was fully programmable, which meant that you could upload programs to both the vertex buffer and the fragment buffer, which meant you could do some pretty cool custom effects with vertex animation and texture data and so on. And what's strange about this is now we have pretty much the same technology in our phones. We pretty much have same sort of performance. The iPhone 3GS was in fact the first phone to come out which had the OpenGL ES2 spec as standard. And since then, this standard has been adopted by pretty much every new mobile device, every new personal device that's come out in the last few years. I know it's only 3 years old, but you know things move fast in this world somehow. So it was still very impressive for its day, and it still performs very nicely compared to the hardware that comes out these days. And so, where does this leave us? We have a CPU and a GPU, and we have the issue is being able to balance all of these components effectively to produce good performance on a variety of devices. So if we're talking about performance, we really need to sort of look at bottlenecks. In previous times when we weren't trying to program the GPU, you'd just be worrying about CPU performance. And it's the same with the Flash player in Flash 10 and below. All you ever needed to worry about was how much your CPU was being consumed. And if it was being consumed too much, the frame rate would go down. So you'd take a few routines out and the frame rate would go back up again. And it was pretty linear. But now we have the GPU to worry about. Things kind of, things might kick off here. The GPU might get angry at the CPU and vice versa. And you have to think about a bus which traffics the data in between the CPU and the GPU. And then they've both got their own separate memory systems. The GPU runs on its own VRAM or DRAM or whatever we want to call it these days. And obviously the CPU has system RAM, and these two are also completely separate and also have separate limits. So the issue obviously is that you're only as strong as the weakest link. And things can start throttling each other very swiftly if you don't know how to manage all the various limitations. So how do we get through this nest of bottlenecks? The thing that we have to define is what complexity is now, because previously complexity in your program, which was just CPU driven, was just about the number of instructions you were trying to do per frame. And it's a fairly simple concept to understand. But when you're dealing with GPU, one of the first things you need to consider is something called vertex density. And GPUs basically render everything as triangles. And these triangles are made up of vertices, one for each point on the triangle. And there can only be so many vertices handled per frame by a GPU. So you need to be sure that you limit that to below what the GPU can handle. Otherwise, your system will start being throttled by that part of the processing. There's also a similar limitation for texture density. You can only have so much texture data on screen at any one frame. And because of the way OpenGL works, this is a frame-dependent metric. It's something which changes every single frame you re-render, because OpenGL is a stateless system. It doesn't store anything for later use. It rewrites its frame buffer every single frame. So texture density per frame is an important thing to consider. And it's part of the reason why using MIP maps are such a good idea. MIP maps are a way of compressing texture data so that you have smaller resolutions. It's by powers of 2, so you have a half resolution, a quarter resolution, an eighth resolution image of your textures. And then when the GPU comes to rendering them, it picks the most suitable one for the triangle scaling that it's rendering. So if the triangle is very far away, it'll use a smaller MIP map for that and consume far less data on the GPU. And the last thing is visibility spectrum. So this is about what you can actually see through your viewport. A lot of the time when we're programming for games, you will have a large extended scene with tunnels, or maybe an outdoor scene with hills and so on. And most of the time, you don't need everything in that scene to render it to the viewport, because it's all dependent on your position within that scene, your point of view, your camera. And this is something that we need to limit as well. So let's take a look at the visibility spectrum first, and how we can deal with this. Well, if you're dealing with a sort of a world that you can move around, like a sort of first-person shooter style game, you're generally having a few rooms or different areas in the scene that you can move to, and this is basically handled by the CPU. What you actually see is the stuff that needs to be uploaded to the GPU. And so the CPU can be clever about what it actually says to the GPU. This is what you need to render this particular frame. The process is most commonly known as culling, and you can do this a number of ways. Like, for example, in this diagram where you have position A, you're inside this hall, and if the CPU is clever, it can say to the GPU, we only need this amount of data to render this frame. We only need the graphics, the textures, and the vertices from the hall so that we can render the whole scene, because everything else is hidden. And there's a number of techniques you can use for this. You can use things like cell culling, which or partitioning. You can define an area and then assign to that area a number of other areas of the scene that are visible from that viewpoint. And this is something that we actually have in Away3D 4.1, although at the moment it's a manual process. So you can define a cell for your partition, which is basically a cubic area in 3D space. And then you can say what other cells are visible. So you create an entire network of cells for your entire game, and you can say which cell is visible from any other cell. This is something that you wouldn't necessarily want to calculate at runtime. So in the future, we're hoping to be able to provide some routines that will actually do this automatically for you in a similar way to how Unity does it, for example. So next, so when we go back to our three properties, the other two are texture density and vertex density. And these are handled by two different areas of the graphics chip. Texture density is handled by the fragment unit, or fragment shader rather, which is obviously these days now a programmable thing. And it will take a certain amount of time to render that for the frame that you're currently viewing. Similarly, the vertex data goes to the vertex unit, which will deal with the those calculations that are required to actually project the vertices from 3D space into your screen space. And these two operations occur in parallel. So the operation that takes the longest will be the defining limitation of your system. And you'll notice this, and there's ways to actually detect for this, as we'll see a little later with the examples, to be able to spot whether or not you're being transform bound when you have too much vertex processing going on, or whether you're fill rate bound where you have too much fragment going on, fragment shader going on. This is like an example to show you how these things can vary even across a single model. The purple areas are where we have a vertex-bound portion of the scene, and the orange areas are where we have a fill rate-bound area of the scene. And of course, the fill rate has many more pixels to fill than it does vertices to transform, and the transform-bound area has many more vertices. So when we're actually thinking about vertices, there's also one other consideration, which is that the vertices that you get from a model that's, say, being given to you by a 3D designer do not necessarily equal the number of vertices that the GPU will process. And this is to do with the way data is stored. On a model, certain pieces of data can be shared between vertices, or what they're calling vertices in their model. But the GPU can't do that. It needs to have unique data for each vertex because it's a parallel process. It can't communicate between vertex calculations. And so for that reason, sometimes the amount of vertices that you actually require the GPU to calculate can increase quite considerably. The most common is when you have a material that's shared, a mesh that shares two different materials. In this case, you'll have a seam which appears somewhere on the model, and this will multiply the number of vertices that the GPU needs to actually do its calculations, because it will duplicate the vertices that share a position, but that have different materials assigned to them. Similarly, if you have different UV information along a seam of your model, then these will also be split in the GPU. And there's also a similar situation when you deal with shading groups, or smoothing groups, sometimes people refer to them as. If you have different vertex normal information, which is representing the normal that is used for lighting in a dynamic lighting in a scene, then again you have to split this information inside the GPU so that the vertex has a unique piece of information for every vertex in the GPU data. And of course that rapidly splits your model into many more vertices. So it's worth trying to minimize these seams when your modeler is building a resource that needs to be rendered like this in real time. So this is just a recap, really. We have CPU over here on the left, which has its bottleneck is defined by the culling processing that it's trying to do, as well as everything else, any kind of game, AI or whatever. And that has a limitation there. The system bus, which is passing the information to the GPU, has a maximum throughput, although admittedly on modern desktop machines this is of the order of gigabytes per second. But mobile devices have quite a limiting factor in some of this, so the amount of actual mesh vertex data and texture data that's going through there can cause slowdowns or hiccups to occur in your game. And then you have the vertex unit and the raster unit, which deals with vertex shaders and fragment shaders. So, what sort of techniques can we apply? Well, a good quote that I like from Michael Abrash, who is one of the fathers of the Quake engine, was that it's more important to know what to optimize than how to optimize. And obviously what this means is you need to know how these things are behaving rather than just blindly taking out vertices and stripping down meshes and textures. You need to know where these bottlenecks are occurring. So something that we can actually use right now in our Flash projects or in our Away3D projects is Adobe Scout. It actually does quite a nice job of solving some of this detective work that we have to do. So what I wanted to do was just take you through a few examples and show you what's happening in Adobe Scout and how we might be able to optimize as a result. So the first one I want to show is something that we released with the 4.1, it's over there, something we released with the 4.1 version of Away3D called the Sponsor Multipass Demo. I know this is just quite a complex model. It actually originates from Crytek. This is like a test model that they use on their engine. We are using this with some advanced shading techniques that are now available in 4.1 as like a sort of test for performance. Let me find, these have all gone to pot. Hang on a sec. Yep, that's the one. So, oh, sorry, I need to fire up Scout first. So I'll launch Adobe Scout. Oh, now, is this going to fit? Yeah, it looks all right. Just about. So I'll run this. This has been specially compiled using the telemetry option that's now available in Flash Builder 4.7. And what this does is give you a lot of extra information that Scout wouldn't normally be able to pick up, as you'll see. So this is the starting point of the demo. You just see this part of the scene. And we can see that we're sort of rumbling along a little bit under the red line. The red line is the desired frame rate that we want to try and achieve, and anything that comes in below that means that you're achieving that frame rate. And I think this is running at 30 frames a second. So if I move about here, we start to see things happening. If I move, say, forward, we see that the amount of processing, now the blue part of this diagram is the amount of time that the action script is taking to process. So this is a CPU calculation. The gray bar above it which you can just about see there, just below the red line, is the amount of time that the CPU is waiting for the GPU to finish doing what it's doing. So if you find that the GPU is overblown and it can't quite manage what you're telling it to do, then you'll see this gray line go up as well, and you'll know that there's a problem there. So if we move back from here and sort of take in more of the scene, we suddenly see that the blue line is going above the red line of our optimum frame rate. And if we also change the mode here for a second, so that instead of a multi-pass demo, we're running it as a single pass, simpler texture. This takes out some of the detail. You see that we don't get quite such a nice image, but you also see that the frame rate suddenly pops back to what it should be, around 30 frames a second. So if we just sort of stop that for a second so we can analyze what's going on here, it's actually quite revealing as to what you want to optimize. So when it's well below what we want it to be, and this is running very well, we can select a range of frames, and it'll actually take the average of the performance of all functions that go on in here. And this little function tree diagram down here is very useful. If I switch this from bottom down to top up, then what it will do is it will group all the functions in terms of their name and give you an overall amount of how much each is taking in percentage terms as well as real terms. So I can see here that, oh, sorry, I needed that the other way up. Bottom up, yeah, that's what I want. So bottom up will take the functions as they are unique, the collecting all of the passes that are occurring within that one frame. And you can kind of see that the biggest drain on performance is draw triangles. This is the GPU command that's sending the data from the CPU to the GPU, and this is taking up 27% of our total frame budget. But if we move over to somewhere where we have a much slower frame rate than we want, so a higher amount of processing going on, and we do the same thing, we can see that the draw triangles thing has shot up hugely. And this is because that this scene is composed of a lot of different independent meshes and a lot of different independent textures. So as we see more of the scene, more and more of it is being pushed to the GPU. And that's taking up CPU time, actually collating that all together. If we actually have a look down here on the right, we can see an average of the stage draw calls per present, which is essentially per frame buffer clear, where it's another name for per frame, really. And we've got over 1,000 draw calls going on, whereas if we actually go back to here and select an area, we can see that this is only 214. So the performance limitation here is the fact that we have fragmented data. The GPU doesn't like to have a lot of things being told to do a lot of things at once. It wants to be able to just do few things that are bundled together. So a large amount of data isn't a problem, but a large amount of things to do, a large amount of draw calls in this case, will become a problem. So one of the ways we could optimize this is by reducing the number of meshes in the scene, combining a few together. And you'd still have the same number of vertices, but it wouldn't be a problem because the number of draw calls that actually requires is less. You can also see over here where we switch off the higher quality materials, we're also getting a slightly lower amount of stage 3D calls, draw calls. And this is because when you're dealing with higher quality textures, the renderer actually has to do a number of passes over the actual model rather than just one pass. So when you're dealing with lower end systems and potentially on things like mobile devices and tablets, which have less performance than desktop, then using a simpler material, type of material, in this case a single pass material, will help with your frame rates hugely, because you're reducing the number of calls that are being made to the GPU as a result. Okay, I should probably speed it up a bit to show you a few more examples. But I might have to skip that. Okay, so next thing that we can consider doing as a performance enhancement is GPU animation. GPU animation makes things a lot faster because you are taking calculations off the CPU and putting them onto the GPU. And in terms of animation, that's to do with the vertex positioning of objects. So this is passing the work to the vertex unit in the GPU. But most modern GPUs can handle quite a lot of processing on that side of things. And so quite often you'll have more power available there than you might have on the CPU after you've done all the other sort of bits and pieces. So if we just run this demo, we can also bring up Scout again. We can see that it's created a new thing here, and this one's running. Now this is running about 400 avatars, and it's running at about 30 frames a second, which isn't too bad. I can zoom in, and again, you'll notice that when I zoom in, the blue line for the amount of time ActionScript's taking is going down. And this is because, again, it's a simple draw call problem. So you can kind of see that while the animation is not causing a performance problem, we've still got a lot of objects on screen at once. So in the latest 4.1 release, one of the things that we've introduced, fairly major feature, is GPU particles. And this allows us to animate the position of individual pieces of, well, individual triangles and also individual collections of triangles without having to resort to multiple draw calls. And this makes a huge difference when you're dealing with performance. So if I just run the particles example here, this is one that you can download from the new release on GitHub and also on our downloads page in Away3D.com. So this is running at 60 frames a second rather than 30 frames a second, which is what the night one was. And while we're not rendering anything particularly complex, we have around 130,000 particles all animating independently on screen. And this is possible by using the vertex unit as a way of moving vertices around rather than trying to transform them and then upload them as a separate collection of triangles. So you're having just one big batch of data uploaded to the GPU every frame, and it creates a much, much faster result. In fact, if we have a look at what's going on in Scout, you can see that there's next to nothing going on the CPU, which is a really nice thing in the particle system. We can also have more complex particles to allow us to do actual models in the same way. So if I run this demo here, you can see that we have around 500, I think, so a similar number again to the night demo, where they're all shaded and lit and so on. And it's using exactly the same technique. These are being moved and animated on the GPU using the new particle system in Away3D 4.1. So, and again, there you go. You can see virtually no CPU going on at all. And there's a little bit of activity going on the GPU. This is because we're almost reaching the limit of what the vertex unit can do. And essentially, if we try to push it anymore, then we start to see this gray line go all the way above the red line and stay there. But we're just about hitting the limit at the moment, so we're doing all right. Okay. So one of the last things I want to show you is a real-world technique of this in action. And this is actually a version of the game that is now bundled with the Adobe Gaming SDK, which you can download through the Adobe Cloud Service. This is called Invaders, which sounds like you have a Lisp, but that's sort of play on words. We thought it was a good idea at the time. And I will run two versions of this game. Now, the first one is using the current build that you can download from the Adobe Gaming SDK, which is compatible with Away3D 4.0. And the second one is using an optimized version for 4.1, which incorporates some of the effects that we have, like the particle systems now, for GPU processing. So I'll run the first one. Where is it? Here we go. So the idea with this game is pretty much similar to the original Shoot the Invaders, or Invaders. And you can play this on a tablet as well. You actually use the accelerometer for moving around, which makes it a little bit more fun. If you search for Invaders on the iPhone App Store or the Google Play, you'll be able to get a version of this. And it runs very nicely on even older hardware like the iPhone 3GS. But if we have a look at what's going on in Scout, we can see that we do have areas where we have some activity going on with the CPU, not necessarily going over the red line, but kind of getting close to it and so on. And this is again down to the amount of data that it's having to fragment and push up to the GPU separately. Now I'm going to run the optimized version for Away3D 4.1, and this looks identical in gameplay and the graphics and so on. But we've added a few extra little effects in there as well. And if I close this and have a look at what's going on in Scout for this particular one, you can see that the performance is much, much better. And this will even run on older devices still without any problem with performance, so older mobile devices. So you can kind of see the advantage that this sort of technique gives you. So I'm just about out of time, and I was going to show a quick example of our showreel, but I guess if you're interested in seeing what's possible with Away3D, and you want to have a quick capsule showreel of about 5 minutes long, then have a look on YouTube and you should be able to find it, no problem at all. But yeah, that's pretty much it. I think I've got about 5 minutes for questions, but in the meantime, thank you very much.
Thank you. Thank you for your amazing presentation. And now you can ask your questions. Напоминаю, задавать вопросы только в микрофон.
There we go. Maybe.
Hello, I have a not usual question. Do you know about some other 3D GPU engines like Alternativa platform, Minka, Yogurt, and so on? What can you say about some cool kick-ass features about Away3D that can it do better than others?
Well, the number one cool kick-ass feature of Away3D is it's free and open source. And some of those other ones that you mentioned there aren't. But of the ones that are open source as well, then I guess ours has had the most sort of evolution in open source form. And we have a very strong community behind us as well. If you only have to go on to our forums on away3d.com, and you can quite easily get answers to any questions you might have just starting out with the engine. But I can't really comment on how features compare. That would be a bit mean. So all I can say is that performance-wise, we're pretty comparable because we still have the same underlying API, the Stage3D API to deal with, and so there's always going to be a hard limit with that. And really, it's about which one you like best and which API you feel most comfortable with. So yeah, is that? I'm not going to get into a feature war or anything, but we do have a lot of cool stuff coming out in 4.1. So if you're interested in new features, definitely check that out. Yes, anyone else?
Hi, I got a kind of related question. What do you think about flash handling GPU?
A GPU?
Yeah.
Well, I know it's not possible at the moment. It would be kind of cool if we had that ability in future, but honestly, I think that at the moment we have got more to gain from CPU optimization with some of the new features that are being proposed for the next generation Flash player. I think that if we can actually optimize those sorts of things, then that's a much better use of time initially. You can get some really good performance out of the CPU, and there's no reason why we shouldn't be able to do that with optimized core routines inside the Flash player itself. So GPU is very cool, but it's not very widely supported at the moment. So really it's the problem when you're dealing with clients having to say what's good about a system. It's going to be difficult to sell that to them for a ubiquitous gaming platform. But it's still very cool. I mean, I've seen Galaxy simulations with it and stuff, and it's it's an awesome thing to play with. Definitely worth checking out.
Thank you. Thank you.
Hello.
Hey.
What about documentation of Away3D and Away physics?
Oh, so we have documentation for Away3D on the site. I think you can go to away3d.com/documentation and see all of that stuff. What do you mean about additional documentation?
I haven't found documentation for Away Physics.
Oh,
What about
okay.
this?
So Away Physics is still a kind of alpha version. We are still working through some issues with the fact that it uses an older Alchemy version, which is now obviously the Flash cross-compiler language, and we're even experimenting with an entirely AS3-based version, which we're actually getting some very nice performance out at the moment. So there's not been so much documentation written because that's in a state of flux. It's changing a little at the moment, but I think that once it's ready, we definitely want to get as good a documentation repository as we can. So we should be working on that, yeah.
Thanks.
There's a guy over there. Oh, right. Go on.
Can I?
Yeah.
So on. One feature that I really want to make in a way, it's a high-level shader language. For example, in Flare 3D, they have Flare FLSL,
FLSL, yeah.
the shader language, and it's hard to write cool features shaders on currently built of Away. Can you say something about it?
Yeah, so we operate on an API basis rather than a purely shader hacking basis, and that's mainly because we feel that it provides more value to people who are using Away3D. Sure, you can't do crazy experimental stuff, but it's not limiting those people who want to do crazy experimental stuff. You just have to dig into the API a bit more, and the system that we have uses a series of shader methods and then shader animation objects which you can combine together to produce your GPU effect. And if you want to extend those APIs, then there's nothing stopping you writing egal code and so on. But as for actually developing our own shader language, I think we'll probably wait until possibly GLSL support becomes a little bit better for the Flash player, because I don't really see a point in inventing yet another standard. We already have a standard with OpenGL, and I think that that should be a little bit more widely supported in the future.
Just for Away Physics, one question. Will there some solutions also for server-side synchronization of Away Physics?
Server-side? Oh, you mean like server-side physics?
Like if I want to do the race game in Flash, but then I want to do it multiplier with same physics code in the way it works in the same way.
Yes.
Also, will you create some solutions also for the server side, for the physics?
I don't know, that's a tricky one. I'd probably have to ask Thibaut about that, but he's gone. I don't know. You should grab me later, though, and maybe we can talk about it a bit more. But I don't have an answer for you right away, unfortunately. I will be around for the rest of the conference, so if you see me and you haven't had a chance to ask a question, please do come up to me and ask your question, and I will do my best. But yes, thank you very much.